I'd like to tell you about the most wonderful of all chemical changes, the chemistry of the creation and the chemistry which keeps us alive today. It's a story which has an unpromising start with a primitive earth, stormy seas, barren land and sky, all dead as a dodo. But the seas gave forth fish, the land, the fowl of the air, the beasts of the field, and all manner of living things, until eventually it reached that peak of natural selection, you and me. Well, what's so remarkable about these chemical changes is that they are a story of increasing order, order arising from disorder, arising out of chaos. They represent, as a scientist would put it, a decrease of entropy. And that's contrary to what we find in our common experience, isn't it? It's even contrary to what we find in the chemical laboratory. If we carry out most chemical reactions, things tend to finish up more mixed up than they started. Let's carry out a chemical reaction to show you what I mean. And I shall take the formula for this reaction from no less an authority than William Shakespeare. And here is his reaction vessel, the cauldron from, the witch's cauldron from Macbeth. Fillet of a fenny snake, in the cauldron boil and bake. Eye of newt and toe of frog, wool of bat and tongue of dog. I had a bit of difficulty getting some of the ingredients for this experiment, and one has to make do with modern equivalents in some cases, but they'll serve our purpose equally well. Adder's fork and blind worm's sting. Adder's forks are very rare these days. Lizard's leg and owlet's wing. For a charm of powerful trouble, in the cauldron boil and bubble. Black spirits and white, red spirits and grey. Mingle, mingle. Mingle, you that mingle may. Well, that's a remarkable bit of chemistry, isn't it? And what is the result? A most awful mess. No little men, no kings, no Banquo, just a mess, just disorder. And that, I'm afraid, is what happens to most of us chemists, unless we're a little more careful. And it's what happens in the more ordinary, familiar world. If I take a nice ordered box of chocolates like this, and I hand you some, and I'm a bit careless, they become disordered. And they're not going to become ordered again without some outside influence. Would you like to be an outside influence? Would you like to pick them up? What's your name?
Stephen.
Now, Stephen is my outside influence. Here you are, then. Now, you pick them up and put them back into order. You create order from disorder. Go on. Keep picking them up. Here you are. Pick them all up. You can have them if you pick them up. Some incentive is necessary. Well, you see, an outside influence can do this. Pick them all up. An outside influence can do this, can create order. Thank you, Stephen. You go away and eat those after the lecture, if you don't mind. Make me hungry if I see you eating them now. Would you like to keep them? Here's the lid. There you are. Thank you very much. Whilst... Now, you see, the disorder of the universe is somewhat more difficult to organize than the disorder of a box of chocolates, and Stephen probably couldn't manage it by himself. But it was natural for the early people, the early men, who tried to explain how all this wonderful miracle of life happens, to think of an outside influence like Stephen, creating the order from the disorder. And of course, what they thought of was a God who could create order from disorder. And the Judeo-Christian religion did more than that. It explained how God brought it about. And if I could read you the first 3 verses of the Bible, better still, somebody else read it. Would you like to read it for me? Come and stand here and read it for us. The first 3 verses of Genesis. What's your name?
Kira.
Kira.
In the beginning, God created the heaven and the earth. And the earth was without form and void, and darkness was upon the face of the deep. The Spirit of God moved upon the face of the waters. And God said, "Let there be light." And there was light.
Thank you very much, Kira. God said, "Let there be light," and there was light. And that was the beginning. Without that light on the first day, the rest could not have happened. And that light, of course, was the sun. We live not just in a chemical world, a world of chemical change. We live in a photochemical world, a world of change which occurs under the influence of light, under the influence of a sunbeam. We live in a sunbeam, and that sunbeam is the creator of all of us. And it's that sunbeam that I want to talk about. And we can't do better now than look at a sunbeam and ask what it is. Now, on a December afternoon in the middle of London, sunbeams are rather rare. And I am finding it very difficult to provide real ones, but Mr. Coates here has the nearest thing. He has the first electric light. It's a carbon arc discovered by Sir Humphrey Davy here in the Royal Institution. And it's not a bad approximation. It's somewhat different, and I'll tell you how it's different later. But it will serve our purpose. And I now want to repeat the famous experiment of one of the most famous scientists who ever lived, Sir Isaac Newton. He bought a wedge of glass, a prism, at Midsummer Fair in Cambridge, and he took it back to his room in Trinity College, and he put all the shutters down, and he bored a little hole in the shutter, and it was sunny in Cambridge, fortunately, and a sunbeam came through and arrived on the wall of his room like that. We made it into a slit so that you can see it better. Now, in the beam, he placed a prism, and that was deflected across here, and it was not only deflected, but you see it became a sequence of colors, which I can throw on the screen there. And Newton said, what is happening is that white light is a mixture of colors, and the colors are being bent by the prism by different amounts. And he did another important experiment. He put a second prism in the red beam and showed that it is deflected further, but there is no further change in the color. So he said it's not something happening in the prism, it's that light is white light, a sunbeam is a mixture of colors, and the colors are separated in the prism. Well, that tells us something about the sunbeam. I call that a spectrum, and I shall keep calling it a spectrum. Perhaps you call it something else. What do you call this band of colors? A rainbow. And that's in fact what a rainbow is. Here is a raindrop, big raindrop, rather nice one made of glass. And if you look at a rainbow, you're looking at a lot of raindrops. And where is the sun? It's over there, isn't it? So the sun comes in from behind, is reflected at the back of the raindrop, and comes back, and you see a color. And Mr. Coates will show us that, show us how that happens. Here is his raindrop. The sun is behind, and we're going to shine the light through, and there, round the light, can you see the rainbow? Can you see the rainbow here? All the way around. It's a complete circle if we do the thing, and you don't see the bottom half of the circle normally on the Earth because you're just looking upwards. There is the rainbow. All right, thank you, Bill. Well, then we know that light is a mixture of colors, and now we must ask what light is made of. And I'm going to do another very, very famous experiment which was carried out here in the Royal Institution by Thomas Young in 1801. Isaac Newton, had said he thought light was a stream of particles, rather like bullets from a gun. And Thomas Young favored the other idea that it was a wave, and he proved that it was in this way. He took a light source, shone it through a slit, and then shone it through two more slits. And then he looked at it on a ground glass screen. Now, this is a very difficult experiment for me to show you so that you can all see it. And what we're going to do is to put it onto the camera there, right across the room. And let's see whether we can see what Thomas Young saw. Beautiful, we can. The cameramen have worked very hard on this morning, and I'm delighted to see that. Now, let me show you what Thomas Young did. He put the light through one slit, and you see the light, just a beam of light as you'd expect. Now, we'll close both slits and open the other. You see a beam of light to the right, just as you'd expect. Now, I open both slits, and what do you see? Can you see clearly? Dark and light bands. Well, now that is absolutely amazing, because what happens is I have some light, I shine some more light, and part of the screen goes dark. How can light and light make dark? Well, Thomas Young said, I know how it can, because I've seen it happen on the Emmanuel Pond when the swans went over it. Here is a water tank which Thomas Young used to demonstrate this. If Mr. Coates dips his finger in, we get waves, you see? Okay, right, Bill? Let those settle. Now we're going to have a little oscillator and make waves like this. And now we're going to start this. You see those waves going out? That's all right. Now we start the second oscillator. Now you don't get the sum of the two, you get an interference. And let me give you a little hint. You will see better if you take your stroboscopes out of your pocket. Have you got your stroboscopes? 4 fingers, and do that at about that speed. And you see, can you make it stay still? If you do it about the right speed, you can make that stay still. You see it better. You can see it pretty well without doing that. Now, what I want you to notice is that I'll shine this red spot on. You see between here, white, dark, and going all the way here. So if I put a screen up and down here, I shall see bands, shan't I? White and dark. And that is how waves behave. And Thomas Young said that's why light is a wave. In fact, he illustrated the point. You can illustrate the point in this way. If I have a model here where these two waves are added up to this wave, okay? Now, at the moment, they're over the top of one another, so they're reinforcing. If I move one wave over the other so that they're opposite each other, then they cancel. And if I move it again, they reinforce. And again, they cancel. Every time they get half a wavelength out of step. And so that's what happens when one gets interference of waves in the way that Thomas Young said. Now, the next question we might ask is, what are these waves? I have the white wave bill, please. Are they waves like this, or like the water waves, going along in this way? Or are they waves like sound waves, or like waves in a spring? See, here are waves in a spring, which go along like that. Those are called longitudinal waves, and these are transverse. What's the difference? The difference is that this kind of wave has a direction, hasn't it? See, that's different from that, isn't it? This one hasn't. So if we ask whether light has a direction, if we find light has a direction, then it'll be like that, won't it? Well, let's see how we can do it. If I try, get rid of that, if I try to pass this wave through a couple of gates like this, then if it's the right way up, it will pass through. If it's this way, it won't. If it gets through that one and this is not the right way up, then it can't get through, and even this one, nothing can get through. Now, you can make material. In fact, natural crystals exist which are like this, and you can also make materials like that. Do you know what? Do you know the name of one? Have you Polaroid sunglasses. This is Polaroid. And we can see the effect, just like those gates. Would you like to come out? Oh, okay. You come out and just face the camera. Now, hold that up, will you? Can you see through it all right?
Yeah.
Can you still see through it all right? Fairly well, can't you? Can we see you? I hope. Yes, what's your name?
Giles.
Can we see Giles all right? Yes, there's Giles. There's Giles. Now let's make Giles do a vanishing trick. As I turn that round, he disappears. As I turn it round again, back comes Giles. Thank you very much, Giles. And what we were doing is passing ordinary light, which is a mixture of both kinds, through, and when we cross these, neither kind could get through. So light is a wave like this, and the next question would be, how long is it? How long is a wave of light? Think of this. What's the distance between two waves? Well, we can measure it with a ruler, can't we? Can we? No. Well, let's try. We can, as a matter of fact. If I take the divisions on the ruler, which are very close together, the 64ths of an inch, and then I look at them like that, they become very close together indeed. Now, if I pass a laser beam, a light, any beam will do, but a laser's convenient, along here onto that screen, and I let this beam hit the divisions, the 64th divisions, then can you see on that screen? You can just see one reflection at the moment. I'm not on the, now, you see I'm on the 64th divisions. You see these spots? Those spots are the same kind of thing as we got from the slit experiment of Thomas Young. They're better now because we have a lot of slits. You see, the divisions on the ruler are acting as slits. Now, it would take me just a little time to go through the geometry of this, but it isn't too difficult. If we know the angle there, and the distance there, and this distance between the spots, and the distance of the 64ths of an inch, we can calculate the wavelength of light. And we find, with this red light, that the wavelength is 6/10 of a millionth of a meter. I'm going to talk about millionths of a meter quite a bit, and I find it a bit of a mouthful. I tend to spit a bit when I say it, so I'm going to say microns. A micron is a millionth of a meter. And this is 6/10 of a millionth of a micron, and if I measure blue light, I find it's about 4/10. It's about half the wavelength of red light. Well, red light you can see out to about 7.77/10. So blue light is about half the wavelength. Now, one more question. which is rather important. Well, it may occur to you, why then, what happens, why don't we have shorter wavelengths than 0.4 and longer than 0.7? Well, the answer is we do, but we can't see them. We can only see that band of wavelengths. Let's have a look at them again. Here is our spectrum again, and the wavelengths from red to blue we know now. And what I want to show you, if I can find my clean, newly washed handkerchief, what I want to show you is that there is something on the blue side which we haven't been able to see. See what happens when I put my handkerchief there? You see, I put this as a handkerchief, and you see some more blue on the left. That isn't visible, it's ultraviolet. But the ultraviolet is making my handkerchief fluoresce. And so we know there's some ultraviolet down there. Can I have the lights, please? Thank you. Now we want to look at, oh yes, we've got a nice thing here. Now, what about the other end? That's the ultraviolet. What about the other end of the spectrum? And where is all the energy that's coming in this sunbeam? Let's have a look at the other end in another way. I'm going to measure, this is a little instrument called a thermopile, which will measure the energy. And I can move it along over the spectrum, like this. And let's have that card. Thank you, Jean. What I'm going to do now, since we know this, I'm going to put a spectrum above. Here's our spectrum, the real one we're making. I'm going to put this one above it. And these are the wavelengths in microns which we've talked about, 0.4 to 0.7. Now I want somebody to come and see where most of the energy is. It's going to be right off the scale there, but it doesn't matter. Now, would somebody like to do that? You're quite near. Can you manage to come around, get round here? Just step over this. Now, what I'd like you to do is, here's the meter, you see. Would you like to wind that along very gently and tell me when it reaches a maximum? Now, hold on to the base, will you? Don't put your hand there. Hold on to the base. That's fine. Lovely. Now, wind it along. Well, now you see it's reading almost 0. Stop there a minute. We're in the green. It's still reading 0. Go on further. Red, still reading 0. Where do you suppose the energy is? Red? None? Go on. Nearly 0, very little. Now it's beginning to go up, right up, and we're past the red. We're going in far beyond the red. Go on. Still going up your meter, almost over the top, and go on. Coming over the top. Go on, further still, and now it goes down again. Thank you very much for a rather difficult one. That's worked very nicely. And what I've done here on this graph is draw the energy against the wavelength that we have just measured very approximately, but very nicely. And I've drawn it for a lamp, which is at 3,700 degrees Kelvin, which is what that lamp is. It's not quite the same as the sun, the carbon arc. It's 3,000 degrees Kelvin. Do you not like degrees Kelvin? Well, I'm going to use them. I've got to use one kind of degree. I'm going to use Kelvin, and if you don't like them, then just subtract 273 degrees, and you can have your favorite centigrade. So these are the degrees Kelvin. Now, I want to show you that just one other graph for if I were able to take a lamp of 6,000 degrees Kelvin, it would look like that. I can't, but if I did, it would look like that. And I show that one to you because it's a very important one to us, as you'll see in a moment, because that's the temperature of the sun. It's much more energy, much more than I've drawn. It goes right up to the ceiling. But the important thing is it's moved along. And where is the maximum now? In the green. And why do you think that is? Because our eyes were sensible enough to develop in a way where they could see the maximum light from the sun. And that's what sunlight is like. So now we're in a position, we know what a sunbeam is, we're in a position to look at a real sunbeam. Let's have a look at the sun himself. The sun is a nuclear fusion reactor 93 million miles away. There's its bubbling surface, the flares on the surface. And those are the prominences, shooting out to a distance greater than the moon from the Earth. That's the sun, a nuclear fusion reactor at a temperature of several millions of degrees in the center, but fortunately somewhat less on the outside, but still 6,000 degrees as I have here. The sunbeams come 93 million miles to us in 8.5 minutes and arrive at the outside of the atmosphere. You just hang on to that one, Jean, thank you. I'll take away this so that it's less confusing. Arrive at the outside of the atmosphere in their pristine state, looking somewhat like that. But by the time they arrive at the surface of the Earth, they are pretty tattered. They look like that. They've lost perhaps half of their energy, and there are holes here in the infrared. And I want to ask, that's the real sunbeam which we see, and I want to ask why that is. What happens to the poor old sunbeam as it comes towards us? Well, of course, it goes through the atmosphere. I haven't had an atmosphere on here before, and if I did have the atmosphere, you wouldn't see it really, because it would only be 2 millimeters thick. So let's blow up a little bit here so that we can see better what we're doing, and put the sky, the atmosphere, over the Earth. Now, to get him straight, Jean, pull it down a little bit. Right. And now let's put on a sunbeam coming from our sun here. Oh, yes, Jean wants us to have a few clouds. But let's have our sunbeam coming through a nice, clear blue sky, because otherwise what I have to say gets... We'll deal with clouds later. But there we are. That's what we're talking about. Now, what I've shown here is the spectrum of all the colors, and I've put the infrared on as well, and the ultraviolet. I didn't know what color to put those, because you can't see them anyway. They're represented by these waves here. Now, what I want to ask is why, as it comes through the atmosphere, does the sunbeam get tattered? And there are two reasons for this. Partly the light is scattered, and partly the light is absorbed. And let's talk about those in turn. If I have a bit of white card, and I shine white light on it, the light is scattered, isn't it? If I have little white bits of paper, it's scattered. If I have even drops of water, it's scattered. Here I have some drops of water, a boiling kettle, and rather like a cloud, condensed drops of liquid water forming a cloud. Now I should switch the light on, and you can see the scattering of the light, and it's white, because those particles of steam are fairly big, and they just reflect like paper. But now if I make some smoke here of ammonium chloride, which has much smaller particles, watch. What's the difference between the two? This is blue, isn't it? Yeah. That's white, and this is blue. Now, that is why the sky is blue. Because the sky is made up of an atmosphere of very, very little particles, air, molecules. And the light, the blue light, because it's a short wavelength, is scattered better. The particles are smaller than the wavelength of light, and the blue light is scattered better than the red light. It interacts more. And it was Professor Tyndall working here in the Royal, he was the resident professor here in the Royal Institution after Faraday, and it was he who studied scattering and who explained the blue of the sky. And if you explain the blue of the sky, you get a bonus because you explain the red of the setting sun as well. Let me show you a setting sun and some blue sky. This is a tube used by Tyndall here, and we're going to shine a light through the tube. And then, at the moment, you see the light is going straight through here. Okay, and Mr. Smoke is going to Coates. Mr. Coates is going to smoke. He enjoys this experiment. It comes in the middle of the lecture. And he's going to put some smoke in this tube. And I want you to see how the blue scattering occurs, first of all. And just put there. You see the smoke? That's enough, Bill. You see how the blue scattering occurs there. Can you see that? It's blue, isn't it? But you see how it gets red as it gets beyond here? And that's because all the blue is scattered. And so there's only red left to scatter. Well, now if we go through a longer atmosphere, as we do when the sun sets, it will become redder and redder. Now watch the sun as we put more and more smoke in. Here's the sun. Now we put smoke in. You see it's quite white at the moment. And we're scattering blue light from the smoke. Now it goes red as it goes through more and more atmosphere. And we get more smoke in still. It gets redder and redder until he's set. Right, thank you, Bill. And that... and that explains why the sky is blue and why the sun setting is red. You see, as the sun sets, as he comes down like this and sets, we're here, his light goes through more atmosphere, through a longer path of the atmosphere, so you get more and more scattering. The blue is scattered out, and the red is left behind. Well, now the second, I said there were two reasons why light is removed as it goes through the atmosphere. The first is the scattering, and the second is absorption. That is to say, the waves of light, which are electrical oscillations, the waves of light interact with the oscillating molecules. Let me show you how a wave interacts with an oscillator with this model here. This is, we call this the Vinnicombe wave model. And I have here some little oscillators, which are little weights on springs, like this. And they have a definite frequency, like a pendulum, as they go up and down. Okay? Now let's make those motionless. And I can send a wave across here. And I'm going to send a wave with a long wavelength, first of all. And you see how the wave goes straight through the weights. It doesn't care about them at all, and the weights just go up and down with the wave. Right, stop it. Now I'm going to try to make the waves resonate with this spring, so they're exactly the same frequency. Now I sort of keep one eye on this spring and one eye on this and another eye on you, and we try and get the frequency right. You see they're stopped. They're stopped at those weights. You see the first weight is having a terrible time. He's going up and down like mad because he's absorbing so much of the energy. Some of the energy is being reflected, but he's absorbing so much of it that the very little gets through to the next one. And that's resonance. Thank you. That's resonance of a wave. And now we must ask, what is the oscillator? We know what the wave is as it comes through in the sunbeam. The wave is the wave of light. And thank you. Thank you, Liz. Now, there are a number of molecules in the atmosphere. I'm stuck, Bill. Thank you. A number of molecules in the atmosphere. And the most important to us at the present is water. And you know what water is, what the chemical formula of water is? H2O. Well, there we are, H2O. Oh, this is the oxygen, and it's bent, like this. Now, I'm going to make it oscillate by just pushing it with a bit of wire here at a certain frequency. And you see it oscillating regularly. It's sort of breathing, isn't it? Breathing frequency. The two springs are oscillating at the same frequency. And if I change the frequency to a higher one, you see as I change it, it doesn't know what to do. Now if I change it to a higher frequency, I get a different oscillation. Just a minute. There it is. The antisymmetric oscillation it's called, because one spring is being compressed when the other is expanding. Okay? There are three oscillations like this, three distinct vibrations, frequencies corresponding to the water molecule. Now it's those which interact with the light wave, actually the infrared light wave, and that one which you see there, that particular oscillation, is the one which is responsible for this hole in the atmosphere, this hole in the sunbeam, at 2.7 microns. That plus the one I showed you before, going together, are responsible for that one. And then these others, you see these holes here? These others are harmonics, rather like upper octaves in a sound wave, upper octaves on the piano. And it is that which is taking out most of the infrared light. Carbon dioxide takes out a bit as well. Right? Now, let us go to the ultraviolet end. The ultraviolet side isn't absorbed by vibrating molecules like this because they vibrate too slowly for it. Remember, the ultraviolet's very fast. But there is something in the atoms which vibrate very quickly. And that is, do you know what an atom is made of? It's a nucleus, and what goes around the nucleus? Electrons. Here is an atom. Let me show you an atom with one electron going around it. There you are. That's just what you thought an atom was, isn't it? And this is what you thought a red wave was, I hope. We're just looking at one electron happily going round in its orbit with a definite frequency. And if our light is of the right frequency as it goes along here, it will be absorbed by the atom like that, and the electron jumps up to a higher orbit. And it stays there looking around for about 1/1000th of a second, and then it emits the photon again, and the electron drops back into the lower orbit. Well, that is an oscillation of there's a resonance of the light wave you see with the electron. But now I have to tell you something absolutely terrible. You notice there's something funny, perhaps, about that model. The electron didn't just climb up, did it? As the wave came along, the electron didn't climb up gradually. It jumped into a new orbit, and there's nothing in between. And that is because light isn't... we've wasted our time, haven't we? Light isn't a wave. Well, it is a wave, and yet it isn't always a wave. Newton said it was particles, and he was right, but he wasn't quite right. Light has wave properties and particle properties, and it really isn't quite like anything on Earth that we can see or imagine. But it is not sufficient to just think of light just as waves. We must think of it as particles. And we must think of light as a quantum, a packet of waves of a definite size and energy. And I want to show you an experiment which illustrates that, because this is one of the classic experiments which founded the quantum theory, and it's an experiment which was explained by Einstein himself. I have a gold leaf electroscope here. I think you're all such modern people that you haven't seen a gold leaf electroscope, some of you. But it's a very nice way of measuring a charge. If I put a charge by induction on this plate, the charge on the gold leaves make them repel each other. Can you see that? You see how they've repelled, and if I discharge it, they go down again. So I'm going to charge that, and that is charged negatively. Now this is what I want to show you first. This is a zinc plate, just a metal zinc. And if I shine light on it, it loses its charge. And that means the electrons are being kicked out of the zinc metal. Now, just to show that it is electrons, let me do another experiment. I'm going to rub a piece of ebonite with a cat. And this makes a positive charge, which allows me to, a negative charge, which allows me now to induce a positive charge on the plate. So, now let me repeat the experiment. Nothing happens. So, it can't kick out positive charges, it can only kick out negative ones, kick out electrons, all right? Now, the final experiment I want to do is to put a negative charge on again so that electrons can be kicked out. Silk, overusing the cat. There we are. Now, first of all, I'll put in front of this some black quartz. It's quite black, but it is transparent to ultraviolet light. Now put that in there, take out the screen, and you see it's discharged at almost the same rate as before. Now finally, I'm just going to put a piece of transparent glass in front, charge again. Piece of transparent glass in front, pull out the shutter, and it stays up, doesn't discharge. Because glass is opaque, it's absolutely jet black to ultraviolet light. And it's only the ultraviolet light which does it. So what have we learned from that? We've learned from that, you see, it's rather remarkable because there's far more red and infrared, isn't there? We saw that, we measured it, you measured it, didn't you? Far more red and infrared, and yet the blue and the ultraviolet are what do the trick here. So there must be more to it than just the amount of energy in it. And the answer is that an ultraviolet wave packet, which we call a photon, an ultraviolet photon can give a bigger kick than a red photon. And the energy that it gives is proportional, in fact, to the frequency of the wave. And I'm going to put this is one of the most important equations in the world, and so it's quite appropriate that I should put it above the world. That is the basic equation of the quantum theory of light, and it tells us that the energy is proportional to, h is a constant, it's called Planck's constant, to n, the number of waves a second, the frequency. And the photon of light is hn, and its energy is E. This same effect of kicking, that was kicking electrons out of the metal. The same effect can be shown in a chemical reaction. We should be talking a lot about chemical reactions later. Same effect can be shown in a chemical reaction. This in here, I have a tube of chlorine, test tube of chlorine, and hydrogen, and I've got a filter of red light around it. And I'm going to shine a filter which filters out all except the red light. I'm going to shine a light on that, and nothing happens. If now I remove the filter, something happens. something happens because, again, the molecules of chlorine can only absorb the ultraviolet light, and there's only enough energy in those ultraviolet photons to split the atoms and split the molecules and break them into atoms. And then they subsequently react with the hydrogen, and you've got a bit of a bang, which is the explosion making hydrogen chloride. So now to sum up, we have, at this point, we have the sunbeam coming in to the Earth through the atmosphere, and when it meets when the infrared meets water molecules, it is partially absorbed. And when the ultraviolet meets the ozone layer, that is also partially absorbed. So that is the shape, that is the kind of sunbeam which eventually comes through here. So one thing that worries me is we never measured the velocity of light, did we? It'd be nice to measure the velocity of light, wouldn't it? Well, I think we ought to know what the velocity of light is, because I've been telling you how long it takes to come from the sun. So there are many ways of measuring it. It's really quite easy to measure. But here's a little recording, if we can possibly have it. Here's a little recording which will help us to know how fast light travels. See whether you recognize what it is. First of all, Houston speaks.
Altitude 4200.
Houston, you're go for landing, over.
Now Neil Armstrong.
Go for landing, 3,000 feet.
That, I wonder whether you recognize it. It's a recording from Apollo.
Landing on the moon.
That's right, and that's right, and it's the first one. It's Apollo 11, and you remember who the astronaut was? Neil Armstrong. Now, was there anything peculiar about that recording that you noticed?
Oh,
yes.
A little beep on it, didn't it?
Yes, there was a beep and a delay, wasn't there? There was a delay of about 3 seconds between the broadcast from Houston and getting the reply back to Houston. So it must have taken 3 seconds at least, at most. It took 2.5 seconds, in fact, to go to the moon and back. And from that, if we do it accurately, I should tell you that out here, of course, the infrared becomes, do you know what the waves become as I go on down Piccadilly in wavelength? Radio, yes, they become radio waves, and radio waves are electromagnetic just like light, and they travel at the same speed. And the speed, if one calculates it from what I've just done, or by more accurate measurements, is 186,000 miles a second, or 300,000 kilometers a second. And that enables us to say what the number of waves, n, in that formula is. If the speed is 300,000 kilometers a second, and we have a red wavelength of 0.6 microns, how many waves a second are there? You can't do it in your head, perhaps, but it's a terribly big number. It's 500 million waves a second. That's the frequency of red light. So now we see how the sunbeam is absorbed and what it is when it comes down to the surface. We've seen how the sunbeam, the white light of the sunbeam, produces the colors of the atmosphere and the Earth. We've seen how it produces the colors of the rainbow, colors of the blue sky, the red of the setting sun. And now I just finally want to see how it brings more color into our lives as it arrives at the surface of the Earth, because the number of colors around me are wonderful, and all these are being produced somehow from white light. And let's have a look at the ways, one after another. Well, the first way is just that some of the white light is absorbed. And that is why chlorophyll, why leaves are green. This is a solution of chlorophyll which I've extracted from, maybe you can see it's green, I've extracted from leaves, or Elizabeth has. Now, why is it green? What coloured light does this absorb? Green, green, green. You're all wrong. Everything but green. Otherwise, you see, I can see green. If I look at a white light, I see green. That means I don't see red and I don't see blue. That's because they are being absorbed by this. And they're being absorbed because the electrons in the chlorophyll molecule, which we shall see later, are picking out the red and the blue waves. And it's the same. Here's some blood. Suspension of blood. Now, what wavelength is that absorbing? Nobody say red. No, again, it's absorbing everything. It's absorbing the blue and the yellow and the green and letting through the red. So that's the first reason that things are coloured, is that the white light is partially absorbed. Just some of the wavelengths absorbed and the others are allowed to go through. That's the first thing. Now, a second rather interesting one is, why is a blue-eyed boy blue? Why does he have blue eyes? Is there anybody who knows that he has blue eyes here? Do you have blue eyes? Let's come and have a look at you. Let's have a look at you. Can the camera have a look at him? See? Oh yes, he has lovely blue eyes. And if they're not blue eyes on your monitor, it's a bad monitor, because I can assure you he has very blue eyes. Now, do you know why your eyes are blue?
No.
Do you think it's because they absorb red light?
Yes.
You do? Well, it could be. I mean, that would be a sensible conclusion. But it isn't. Can anyone guess, by looking at the colour of that and thinking of the colour of something else that we've talked about? The sky. Believe it or not, it's rather surprising. His eyes are blue because they're scattering light. In fact, the iris has a black screen at the back, and there's nothing coloured in his eyes at all. But in the iris, floating around in the iris, are little particles of protein. And as he gets older, those little particles of protein will get bigger, and his eyes will go green or something. This is what often happens anyway. Most babies' eyes are blue, and the particles grow. As the particles get bigger, the blueness disappears. But that's why it is. It's just what Tyndall explained for the blue sky. His eyes are blue for the same reason that the sky is blue, because of scattering. Thank you very much. I hope you keep your blue eyes. Now, there's a third cause of colour in our lives, and that is interference. Here is a peacock's feather. One of the most beautiful examples of it. We'll see some others in a moment. And you see how it's what people call an iridescent colour. And furthermore, you probably see the colour changes. The colour changes as I turn it. It goes from blue to green. Blue to green. Is that better? There. Now, that is a third. There's no dye in that. No dye in that. There's a third reason why that sort of colour arises. And I've talked about it. I wonder whether you can remember you can guess what it is. It's interference. It's interference of the kind that Thomas Young discovered with the two slits. You get interference in just the same way. If you shine light onto a thin film. And on this feather is a thin film. Here is the thin film. If I shine light onto that, it's reflected from two surfaces, the bottom and the top. And if it's reflected in phase like this, I can see it. But if I have a blue wave, which is a shorter wavelength, in this particular case, it wouldn't be reflected at that distance, at that thickness. That's got to be quarter of a wavelength to get the reflection matching. Here you see the waves are cancelling out. And that, of course, is what happens with an oil film and a soap bubble. Mr. Coates will show us a soap bubble here. He puts the soap film on a little wire like that. We're going to reflect light from it, just as I showed you on that diagram. Okay, now I drop the lights. And I hope on this screen, let me remove the laser spot. Now you see, it's a fairly thick film at the moment, but as the soap falls down, you're seeing it upside down, so it's falling down towards the top. It's all done by lenses and mirrors. But you see the beautiful colors appearing now? I'll get it in focus. And you see the different colors are due to the different thicknesses. We only get reinforcement at certain thicknesses, and so at one thickness blue is reinforced, another one red, and so on. And so we get this swirl of colors as the thickness of the soap film changes and as we get interference to different extents with different colors. Thank you, Bill. Well, now, one example I'd like to show you, which exhibits in his masculine splendor all three means of making color in his head, is a very seasonable gentleman, the turkey. Now, turkeys get a little bit nervous around Christmas time. But he's not too bad. He's quite enjoying it. And I want you to have a look at the various colors that he displays. First of all, okay, boy, his wattles, these red wattles here. The red of those is caused by blood, hemoglobin. And so that's the first mechanism of making color, the absorption of light. Now, secondly, you see around his neck and around here, there's a blue tinge on this part of his neck. And in fact, as he becomes annoyed, there is more blue. He goes quite blue when he gets annoyed, around about here. And that is, well, what do you think that is? Scattering. Jolly good. That is just like the blue-eyed boy. That is the protein in that part of his neck, which is scattering with a black background. And then finally, the interference, the iridescence. Can you just turn round this way a bit, old chap? Because we want to see your beautiful iridescence. I know you'd be showing it off if there was a lady turkey around, but we want to see it too. There, you see these feathers, which are just about as good as the peacock's feathers, and they are producing color because light is being reflected from the upper and the lower surface. So he's very clever. He produces color in all these many ways and displays the splendor of color by scattering, by interference, and by absorption. Well, we've seen how the sunbeam brings not only light to our lives, but color to the world as well. But next time we shall see how it does much more, how it breaks molecules up and puts them together again in the most intricate and marvelous ways so as to build up the substance of living things, of flowers and leaves, of animals, and even of Tom the turkey.